What would they want to see?
Oscillation.
Yes. So for simple harmonic motion, the key concept is that it's motion where the acceleration is proportional to what? No.
Proportional to the number of
No. The acceleration is proportional to the displacement and acts towards the center, to the origin. You know that for simple harmonic motion, that the acceleration is proportional to the displacement from the origin of the motion, and the acceleration always acts towards the origin. This is the definition. In the Markan scheme, they said the acceleration of a body is proportional to its distance from a fixed point and is always directed towards that point. So that's just the thing I just said. And this is also in your notes as well, so we won't bother writing that down to save time. Let's have a look at the calculations now. B. One end of a rectangular metal strip is clamped at the end of the table, and it's vibrating with simple harmonic motion like this. And the distance is 6.5 and the frequency is 15 Hertz. What? What's going on? Oh, fail. Right, let's have a look at the B part here. Yeah. Oh, easy. So how do you get the first part? Let me fix my pen again. Come on, come back. I think it's the cable, because if I...
You know, like John doesn't use the...
Yeah, I'm thinking next time I'm going to take that one. Right. So how do we do B part 1? Yeah. Stupid. T is 1 over F, which is 1 over 15 seconds, which is 1 divided by 15, 0.0667 seconds. Right, that's B part 1. B part 2, what's the maximum acceleration? So that is omega squared A. Well, it's maximum, technically it will be plus, and they usually don't care about the direction, so you can drop the plus or minus. But technically it would be the plus if you want to be technical. The omega is 2 pi over t, and the amplitude is given. What's the amplitude? Says it in the question. 6.5 millimeters. Oh, of course. So I got an acceleration of 57.7 meters per second squared. Let me double check that. That is correct. And it actually says in the marking scheme here, KJ, no need to show plus minus. Okay. Part 3. What is the maximum speed? So do you remember that formula? That is A omega. So again, the omega is 2 pi over t, and the t is 0.0 and that. And then the A is 6.5 milli. Yeah, so the maximum velocity is 0.613 meters per second, which is correct. Next part is, when will this maximum velocity take place? So if you picture this as vibrating up and down on the table, let's say ABC, when is it going its fastest? At B. Yeah, the center of vibration. Okay, part 5. Determine the time taken for the metal strip to move from 4 millimeters above the equilibrium to 4 millimeters below the equilibrium. So this is starts off at 4 millimeters above, and you want to know when will it be 4 millimeters below. So here this is 4 millimeters above. Now this question is actually quite bad because he does not say if it's moving up here. Because imagine this was vibrating up. First it would have to reach its peak and then come down. But if this was on the way down already, then you'd get a shorter time. Now, which do you think he wants here?
Going down.
Free is down with it free.
That doesn't make it go up or down.
Free and no, it's going down, but it moves from a position from up to down.
But it still could be going up. But anyways, if I was to have a guess, I'm going to take it that he meant to say on its way down from 4 above, how long to get to 4 below.
Because in the dark, like above it will be to a position 4 millimeters below.
No, there's nothing in this question that tells me if it's on its way up or down at the beginning. But I'm going to assume it's down because it would make most sense that what happened was he lifted this up to 4 millimeters or whatever and released. Oh no, it's not 4 millimeters. It's 6.5 and released, and it's on its way down. So we'll take it like that it started up here at 6 millimeters and then began going down. So we want the time taken to go from this position to this position. So our formulas we need to use, x equals a cos omega t. Now, do we know what the a is? We do. It's, what is it? 0.0065. And do we know the omega?
Yeah.
We do. It's 2 pi over t. Which is 94.25. Times t. So what we'll do is we'll get the time here, and then we'll get the time here, and then subtract. So here is 0.004 equals 0.0065 cos 94.25 t, and then we have minus 0.004 equals 0.0065 cos 94.25 T1 and T2. Now, please make sure your calculator is in radian mode.
Overall, it should be smaller than 0.06.
It should be smaller than the periodic time, yeah. So, my first time I got T1 is 0.0333 seconds, and then T2, no, it's not that, mistyped. My T1 is 0.0173 seconds, and my T2 is 0.016 seconds, which is totally bad.
You checked your T1 again?
Yes, definitely. No, that's wrong, thank you. My T1 is much smaller than that. T1 is 0.00963 seconds. And T2 is, no, it's not even that. Hold on, I'll fix it now. I'm having calculator issues. 0.00237 seconds. And T2 is, oh my goodness, it's not even that. No, that's T2. And T1 is 0.00963 seconds. Yes, the T2 should be bigger than the T1. So the answer is the difference here. The time to go from position 1 to position 2. So that is 0.014, which is correct. Okay, that one was a bit tricky. Well, it was only tricky because I had trouble solving this on my calculator, but we did this in maths. Okay. Last couple of parts here. Can I go down? Yeah. So what we have here in part 6, few grains of sand are placed at the free end of a metal strip. Determine the maximum amplitude of the vibration if the grains of sand stay on the strip throughout the motion. A few grains of sand are placed on the free end of the metal strip. Determine the maximum amplitude of the vibration if the grains... Oh, right, this is an interesting one. So what's happening here is that you have some sand on the strip here. And you can imagine that if this vibrates too fast, or if it moves too much, the sand will fly off. What's keeping the sand in place? Like, what force is acting on the sand? The weight of the sand, isn't it? Yeah? So I think what you would need here, look, this sand wants to fall at what acceleration? 9.81. So if this metal strip falls faster than 9.81, then the sand is no longer in contact with the metal strip. Can you picture, like, here's the metal strip and here's the sand. If I didn't have the metal strip, this will fall with acceleration of 9.81, right? So if the strip falls with the same acceleration, then the sand will stay on it. Or, if the strip has an acceleration less than 9.81, it will stay on it. But imagine this goes down with 20 meters per second squared, while then the sand is left hanging in the air. So the maximum acceleration needs to be 9.81. And the formula for maximum acceleration is A omega squared. So they want the A here. It's 9.81 over omega squared, which is 2 pi over t squared. So when you put those numbers in, I'll just give you the answer straight away. It's 1.1 times 10 to the minus 3 meters. No, it is, trust me. Right, just have it from the marking scheme. If the acceleration was, if the amplitude was a little bit bigger than this, then what would happen to the sand? It would fall off. The question is, when would this happen in the motion? Yeah, what part of the motion here? A, B, or C? When would this happen? Well, when is the acceleration maximum? Yeah, it would happen at, I think C.
When it changes.
Well, no, sorry, A. A or C? But the reason we use A is because at A it's going down, and at C it will be pushing up into the sand. So it's at the highest, at the top. I know it seems weird, it feels like it should be B because that's when it's moving fastest. But A is when it has the most acceleration. Yep. Okay, lastly, sketch a graph of the displacement against, for babies. Right, the last part here, the graph. Here's the time. Here's the displacement. Now, I think this graph is a little bit wrong because his graph starts at the origin, but of course, well, it only starts at the origin if you flick it, but in real life, probably what happened was somebody lifted the metal strip up and dropped it. That's how I'm going to draw it. So the displacement will be maximum. The only thing to do is he wants you to add in the air resistance. So what happens to the displacement as time goes on? Does it stay the same? It reduces, yeah. So what would the graph look like? Yeah.
Up and down?
Up and down, but also dampen, decreasing. So it'll go like this. That was actually B1 and B2. I mean, that's nearly the exam finished because how many would you need to do in section B? 3 questions. So, happy days, I think. Right, that's B2. We have 1 hour now, or 2. 1 hour. Alright, so next time we'll continue with B3. And B3 also looks really nice, so this is a good one. Yeah, no, come in, Tony. Tony, come in, we're finished.
B4 is the best.
B4?